Okay, so recording is started. So in this session, we look at what's called a Model A system. Is where we wanted to be able to do simulations of different systems. So Riaz has been working on is building up to being able to do the simulation of a stochastic of a system with a stochastic noise in it. So in some sense, the system we're going to talk about today is a little bit simpler. Everything there's no stochasticity in this. Okay, so in physics, there's something called an Ising model, and the idea is that, let's say I have two magnets, and or two things which have something called spin associated with them. And spins which are alike are preferred, and spins which are unalike, which are in the opposite direction, are not preferred. There's in the Ising model, there's an energy penalty for those. Okay, so you have this Ising model, and then what you do is you kind of you do what's called coarse graining. You imagine you take this thing which has discrete spins, and you imagine it a spin as a continuous quantity instead of plus one and minus one. You say in a region, what would the average be? That would be some real number, and so we imagine that real number is a continuous quantity, right? Then we create a create a model based on that idea, and we look at local energies. If you have a local energy density and you integrate it, you get a total energy. And then this is called a free energy in physics. And then we say, well, nature likes to put things in terms of a lowest free energy. So entropy is maximized in nature, and free energies are minimized. Okay, and so then we look at a time evolution of such a system, which would lead to minimization of the free energy. Okay, so let's see how we might do that. So we're going to start from the Ising model, which in some sense motivates this thing, which is called Model A, or a Ginzburg-Landau model. Okay, so we have a set of spins Si, which are arranged in a row. Okay, and each spin takes a value of either +1 or -1. There's no intermediate values. And the spins, which are what we find in nature, or in our model, what we're going to do is we're going to say that the spins can only feel the effect of the spin which is right next to it, either to the left or to the right. So let's say they're on a line, and a spin looks to the left and looks to the right, right, and can only feel the effects of the nearest neighbors. Okay, and we notice that spins that are immediately next to each other, they like to be aligned. So we suppose that that the spin they would both like to be up, or they would both like to be down, spin up or spin down, either +1 or -1. Okay, and they would like to be aligned. Okay, and in the absence of an external magnetic field, it doesn't matter what we call +1 or -1. Right, there's this symmetry in the model that if we changed all the +1 spins to -1 spins, we should get exactly the same energy. Okay. right? So here we build this into our model, right? So here's an energy, and we go from spin 1 to spin 2 to spin 3 to spin 4 and so on, and we add this term. You know, SI is at the ith spin, SI is either +1 or -1. Now multiply it by SI plus 1, which is there a question? Okay. Multiply it by the other spin, which is either +1 or -1. And then if they're like spins, then SI times SI plus 1 will be +1. And that's favorable. So you should make that negative, right? You're lowering the energy when the spin is aligned. And when the spin is unaligned, you are increasing the energy. Okay. So then you add up all these contributions to the energy together, and that gives you the total free energy. And we're using H for Hamiltonian here. Okay. If you've done statistical mechanics, you know why. If you don't, it doesn't matter. Basically, that H is an energy. Okay. And nature would like to minimize this energy. Okay. So if all of the, so tell me, if nature causes a time evolution in such a way, let's say that in the other systems we've considered their boundary conditions or their initial conditions. Let's say there are no other conditions. I haven't fixed any of the spins, neither at the beginning nor at the end nor in the middle of my system. I've got n of these spins. They're free to be +1 or -1. And there's no external magnetic field to flip the spins or anything. So they're merely just flipping back and forth on their own. But I know that nature would like me to have the minimum energy configuration. So what would be the minimal value of H? Let's say there were n spins altogether. What would be the minimal value H that we would have at the end? Once the system has evolved to its minimal energy configuration, what is the minimal value of H? Okay, all right. So if a system in the abstract is you can't see the answer, then the thing to do is to think of the simplest such system with just a few spins. So let's just imagine that there are 2 spins. Okay. So there are 2 spins which are up. All right. So what's my H value? If they're just 2 spins, what's the value of H? And they're both up. What's the value of H?
-1.
Right. Now, let's say one is up and one is down. They're mismatched. What's the value of H?
+1.
+1. So it's a higher value, right? I mean, we've tried to build that into our system, that if there's a misalignment, there's an energy penalty. The energy increases. Okay. What if the spins are both down? They're both -1. What's my value of H?
-1 again.
Okay, so let's say that given enough time, nature will force this, will evolve this system until it reaches a minimum energy configuration. Okay. So now tell me, what will be the value of H at that minimum energy configuration? you said that there were two values for H, right? There's either -1 or +1. So what's the minimum of those two?
-1.
Which configurations give an H of -1? Right. Both spin up or both spin down, give me a minimum configuration. Okay, so in the absence of anything else, one might suppose that there's a 50-50 chance that the system will either evolve to both spins being up or both spins being down, right? It shouldn't stay in this configuration of mismatched spins because, nature doesn't like that. Okay, all right, so for a two-spin system, we worked it out. It's either going to evolve to both up, in which case H is +1, or both down, in which case H is -1. Okay, now let's say there are 3 spins, right? The spins don't wrap around, right? They're in a line. Okay. So now tell me, for 3 spins, what is the minimum value of H?
-2.
Right. If they're all, if I've got 3 spins and they're both up, so +1 times +1 is 1, and then +1 times +1 is 2, and then the negative sign outside the summation, -2. If they're both down, if all 3 are down, again, -1 times -1 is 1 contribution to H, and then -1 times -1 is the other contribution in the summation, and then multiply by the minus sign in front of the summation, the -2. Okay, can you think about what if I have plus, minus, minus, what do I have for H?
Zero.
Yeah. Okay. Can you think of a configuration? Okay. Can you think of a higher energy configuration? What about minus, plus, minus? What do I get? I get 2, right? And if I have minus, minus, plus, I think I have 0, right? Okay. So you can have an energy that's as high as 2. You can have an energy at 0. You can have an energy at -2. You might want to think if you can get any other values. I mean, 3 is small enough that you could just go through all the configurations, right? Right. So how is this system going to end up given enough time?
Wouldn't it just reach negative infinity if you have an infinite number of spin particles?
Yeah. Yeah, you're right, it would. But okay. In the real world, what's going to happen though is that you have temperature, right? And you have some sort of external heat source. And that sort of causes random flips in the spins. So you might not actually, well, so I mean, if we made it a bit more realistic and we allowed contact with the heat source, then there would also be random flips in the spins, which would maybe prevent us from actually reaching the minimum. Okay. And if we had an infinite number of spins, we'd probably go to a continuum model anyways. So, okay. All right. So are we okay with this model? with this Ising model. Okay, so there the spins were in a line. Now, what if I imagine I lay them out evenly along a square? So I have a square grid of spins. Okay, and then maybe the spins on the interior of the square, they can see to the left, to the right, to the front, and to the back. Right, but it basically would be the summation SI prime, where well Sij Si prime J prime, where the pair Ij and the pair I prime J prime are nearest neighbors, and you would sum over that and then multiply by -1, and that would give you the Hamiltonian, or the energy for this system. And again, we would suppose that nature would like to put this in a minimum energy configuration. And in addition, so now we could imagine a three-dimensional, like a cube, right, with the spins evenly distributed within the volume of the cube. Right, so that's basic idea of an Ising model. Okay. Okay, so some aspects of the Ising model which are important. Aligned spins decrease the energy, misaligned spins increasing the energy, and absent any other constraints, the lowest energy for all spins is either +1 or -1. Okay, so as what would happen is you might start off with the spins all random, and then they would start to align locally, right? So here they're all random. I have a random number generator to assign a +1 or a -1 all across this thing. There are some places where accidentally, you get 4 of them in a row, which are all plus. Here you have, 5 in a row, which are all minus, right? And then the result would likely be that the area, the region where you had more positive spins would grow as the other spins would sort of flip to a line, and where you had -1s, the other ones would flip to a line, and then you would get larger and larger domains of all positive and all negative, and they would eventually meet up with each other, and then one domain would eat the other, and eventually all the spins would align either +1 or -1. Okay. All right. So again, model A, or the Ginzburg-Landau model, sort of tries to take these features and build them into a continuum model. Okay. So I want a continuum model which has the same features. Okay. So I'm going to imagine that my spins are really, really tiny, and I can't measure individual spins. But what I can do is I can look in a small region, and I can do a measurement, and I can get the average of the spins. So I'm going to call that a spin density, right? And that could take values between -1 and +1. Okay. So what I want are these essential features: that the spin density should favor being either in the state +1 or -1. There's an energy penalty for spatial gradients. So if a region of plus spins and a region of minus spins are next to each other, there's an energy penalty, because I want all the spins to be the same, right? And the other thing is, I want this symmetry in my system, that nature doesn't care what I call up or down. And so it'll be the same energy it should be the same energy if I change my mind. And if I call the opposite direction up and down, then the energy should not change. So I want to build these features into a continuum model. Okay. So Ginzburg came up with this gradient term, Landau came up with the polynomial term, and basically this is the Ginzburg-Landau free energy function. Okay, so f of u is the energy density, and this is being done over some v. So you integrate the energy density over the entire volume, and you will get the total energy, which is f of u. Okay, now look at the polynomial part. Ignore the gradient part for a moment. Look at the polynomial part. 1/4 u to the 4th minus 1/2 u squared. And if you work out, supposing I asked you, where are the minimum values of that polynomial? What would you say? Okay, if I ask you to minimize the polynomial 1/4 x to the 4th minus 1/2 x squared, where would the minimum be? Okay, tell me how you would try to find it. If I want to minimize a function of a single variable, how do I find its minimum?
The minimum would occur at 0, right?
Okay, take the derivative, set it equal to 0, right? The derivative with respect to u is u cubed minus u, which is u times u squared minus 1. That means the critical points are at 0, at +1, and at -1, right? Okay, so if you do that little bit of calculus, you'll see that the polynomial part has a minimum for u equals +1 or -1. So there are local minimum at +1, local minimum at -1. There's a local max at x u is equal to 0. And
what is k in the function?
Oh, so kappa is just it just shows you how severe the energy penalty is for a gradient. See, grad u means that the values of u are changing. If the values of u are changing, then the norm of u squared is positive, right? Positive, adding a positive energy is an energy penalty because we're trying to minimize this thing, right? So the bigger you make the value of k, the bigger you make the value of k, the bigger a penalty you have for having transitions from regions of positive spin to regions of negative spin. Okay. Right, which means that it likes to have all the u across the system is made minimal by making it equal, right? Okay, and if you check in here, if you replace all the u's by minus u's, you get exactly the same energy. Okay, so it has all the features that we built into the model. Okay, it's a toy model. I'm not saying that any physical system follows this model exactly. Okay, but it turns out that by working with toy models, we can see qualitative effects that we do often observe in nature. Okay, so the width of interfaces between regions of positive and negative u is controlled by kappa greater than 0. Okay, now what if I set kappa equal to 0? This gradient term disappears. Then what would happen? What would be the minimum for f of u? There are no boundary conditions right now. Okay, what would be the minimum value of f of u? When would that occur? Okay. All right. So once again, the polynomial part is encouraging the system. If you're going to be moving towards a minimum energy, it's saying that values of u should be -1 or they should be +1. That's where the minimum of the polynomial is at any point. Now, if I have different values of u, if I just set +1 or -1 randomly everywhere throughout the system, and I set kappa equal to 0, then I've minimized my system. If I make kappa positive, then the polynomial part says, I want things to be either +1 or -1. And the gradient part says, I want things to be equal across the system. Okay? So by making kappa bigger than 1, we are forcing the system to choose between values of +1 and -1. The polynomial part itself is just saying, please be either +1 or -1. And the gradient says, well, choose between the two of those. Because having +1 and -1 regions next to each other there's an energy penalty for that. Okay. Okay. Now, the larger you make your gradient, so what you're going to have. Now, let's say now I impose boundary conditions. So I've got at one end, I fixed the spin to be +1. So let's say we're just working on a line. I fixed the system to be +1 on the left. And I fixed the system to be -1 on the right. Okay. And I put in random spins everywhere else. And then I allow the system to evolve. We'll talk about how it evolves in a bit, but I allow the system to evolve. What kind, can you tell me qualitatively what the system would evolve to? What would it look like at the end? Okay. At the left end, I have a system which is +1. The system is taking the value +1. And I've fixed that somehow magically. I fixed that. It's always going to be +1 on the left. And there's an energy penalty for difference. Okay, so that's encouraging the region which is just to the right of the left end. That region should be taking what value of u? Because there's an energy penalty for difference. And this left end is fixed at +1. What should be the values of u just to the right of the left end? Okay, imagine two different scenarios, right? Imagine that the system is at the left end is fixed at +1, and to the right of that, I've got a region where the values are also +1. So what's the contribution of the gradient term? What's the gradient of a constant function?
0.
Yeah. Okay. So the gradients. So if the left end is fixed at +1, and then the region next to the left end is also at +1, the gradient is not contributing any energy penalty. And +1 is also one of the values which minimizes the polynomial. Okay. Now imagine another scenario. At the left end, I've got +1, and right next to it, the region is at -1. Okay? Or it's decaying rapidly to -1. Right? So then what would happen? This gradient penalty would be large, right? And so you would have a higher energy configuration. Okay? So if the left end is fixed at +1, the region next to the left end will also like to be at +1. If the right end is fixed at -1, then the region at the right end, near the right end, will also like to be at -1. Okay? So then this region becomes +1, this region is at -1, and then there's a transition as you go from regions of positive U to regions of negative U, right? And this kappa is going to control how steep that region is. If kappa is very small, then the gradient can be large because kappa is very small. And if kappa is very large, then that means that that transition will be very gradual, right? A gradual transition means a small gradient. Okay, so kappa is controlling the width of the interface between regions of positive U and regions of negative U. Okay. All right, so now we come up with a time dynamics or a time evolution for this system, which is rather simplified, right? If this is the Ginzburg-Landau simplified version. The actual time evolution of the system would actually be a little bit more complicated than this. So we do it like this. We say what, to go back to our idea of gradient minimization, if I move in the direction of minus the gradient of that functional, right? So this is functional. Remember, how do we find, right? And so how do we find the gradient? The gradient is given by, I can calculate the gradient by saying f of u plus h is equal to f of u plus the inner product of the gradient, right, with h plus terms of order h squared. When you've got, what's the inner product here? Okay. When you're dealing with function, okay, so when you're dealing with these sort of discrete vectors, the inner product is your usual inner product. And when you're dealing with functions, typically the inner product of u and v is the integral of u times v, right? Because there's no ui vi that you can sum up, right? So you have to integrate u of r or u of x, v of x dx, right? Okay, so the inner product of a vector u with a vector v, in this case the vectors are functions, the inner product of u and v is the integral of u and v over whatever volume we are dealing with. Okay, that's the Euclidean inner product. Okay, so we can find the gradient of that functional. Moving in the direction of minus the gradient of that functional takes us to a lower energy state, and we have this capital gamma which controls how fast that's happening, right? Okay. So the Ginzburg-Landau dynamics is that U does continuous Euclidean steepest descent to the minimum energy state. Okay, now we want to do this numerically. Okay, so we can use a trapezoidal rule for the integrals, right? So if I have integral from a to b f of x dx, you remember what the trapezoidal rule was? It's basically what we've been doing before, right? You divide it up into n subintervals, or you have n points. That then you have, I guess, n minus one subintervals. Let's make the points equally spaced just for convenience. Evaluate the function at these points, right? And then the function rule is you sum up. We're starting our counting from 0. I equals 0 to n minus 2. Fi is the function evaluation at xi times the spacing delta. Okay, so this is the right hand rule. Okay, and we can the trapezoidal rule is a little bit cleaner. So you take 1/2 Fi plus 1 times delta. Okay, so you have to have some numerical integration, basically. All right. So now in terms of what we've seen before, remember we had this, we're going to do this on a line. So if I want to integrate any function, so forget the gradient part for a second. If I just want to integrate some function f, what I'll do is I'll take the vector form of f, the fi's, right? Operate this d0 on it that we've had for the prototypical problem. Multiply it by a vector of n minus 1 ones and times delta. And that's my approximation for the integral of f over that line. Okay. So let's say I want to integrate, say an example. I want to integrate from 0 to L, 1/4 f to the 4th minus 1/2 f squared dx. So f is continuous. How do I approximate this? Okay. Well, the way I approximate it is I'll let u take values u1, u2, u0, u1, u2 up to un minus 1 on those points x0, x1 up to xn minus 1. Okay. So that gives me a vector u minus, so 1/4, that's the u to the 4th means the vector u with every entry raised to the 4th power, minus 1/2 the vector u with every entry raised to the square power. Okay. Then I take my operator d0 on that. And then I take the inner product with a vector which is all ones. And then I multiply by delta. And that's my approximation to this integral, right? That integral is continuous. And this is the numerical approximation to that integral, all right? It's not exactly that integral. So is that okay? All right. Now, what if I have to estimate this? So it's 1/4 f to the 4th minus 1/2 f squared plus kappa over 2 times the derivative of f squared dx. Okay, so I'm going to apply the trapezoidal rule to this. I already have the answer for the polynomial part. So now I want to have the answer for the gradient part. And the gradient part will look like, so it's going to look like this. right? So the first part is what I've already done. Notice that I'm multiplying by delta. That was my spacing between the nodes. And this part would be, well, what's the gradient squared? Just take the grade. D1F is an approximation to the gradient. Take the inner product of D1F with itself. That's like D1F squared. So, oh, sorry, F sub X squared. Okay. And then again, you have to multiply that. You have a kappa over 2 here, and you have to multiply by the spacing delta. Okay. So this is like a Riemann sum for the integral of the gradient. Okay. All right. So now I have to minimize. I have to minimize this functional to get the gradient. And then I'm going to take discrete time steps to get what I want, to get down to the minimum energy state. Okay. So again, in one dimension, this is what it looks like. Now I have to find the gradient. How do I find the gradient? Well, f of u plus h equals f of u plus the gradient at fu with respect to h plus order of h squared. Okay. And if I do all of that, this is what I find. I get f of u plus h equals f of u plus delta u cubed minus u times. Now, this was a d0 of h was on the right-hand side, but when I brought it over to the left, it becomes a transpose. And the same over here, I had a d1 operating on h, but I brought it over to the left, it becomes d1 transpose. Okay, and so these terms, which are with the h, those are the terms of the gradient. Okay. So this is what the gradient is. Now, I've got delta in both terms. So when I'm going to take when I'm going to do gradient descent, I'm going to be multiplying that by some step lambda. So I can absorb that lambda, this delta into that lambda. Okay. So I'm just going to, okay, so that's a misprint there. I'll fix it when I upload the notes. This delta shouldn't be here. And now we can do the time evolution using this scheme. So to get a new u, you take u minus lambda, u cubed u minus u, d0 transpose times that vector of ones, plus that delta shouldn't be there, kappa, d1 transpose, d1u. Okay. And we can see how that system evolves, and we can see what the final configuration is when it stops evolving. Okay, so the evolution will continue until you, presumably until you get to the minimum energy state. And one of the things that people are interested in is how these domains of positive and negative, or the area in which there are interfaces as you're going from a positive domain to a negative domain. People would like to see how those grow with time. Okay. And that's the basic idea. Once again, sorry for giving you a lecture which is out of sequence, but it couldn't, Riaz couldn't be here today. Okay. So basically, the same idea of gradient descent that we used to get approximations to solutions of differential equations. That same idea can be used. You just say my functional represents an energy, and if nature minimizes the energy, I can use the same steepest descent gradient technique to minimize that energy. Okay. All right. So, are there any questions? Okay. If there are no questions, then what I will do is those couple of mistakes that I noted in the slides, I will change those, and so I'll probably be uploading then the revised slides, tomorrow. Okay. Once again, we're at the encouragement of the administration, we'll be finishing up this this course 1 week early. Okay. Okay. So I will see you on Friday, hopefully.